All right. Thank you all for coming. I hope you had a great keynote session. My name is Uttara Sridhar, and I'm here to talk about visibility into serverless applications built using Fargate. I'm also joined with Carly Cindy from Catalytic Data Science, who's going to go into the Catalytic's use case in a bit. OK, here's the agenda of my talk. I'm going to level set this conversation and talk about the sample app. And we'll see how and why we need to use Fargate. And then we'll go into why visibility is important for your serverless applications. And then we'll dive into logging, debugging, monitoring, and look at some best practices and examples in each of those. And then I'll hand it over to Carly to talk about their journey of building their bioinformatic workloads on Fargate. OK, so I'm going to introduce you to a scorekeep application. It's just a tic-tac-toe application. And I'll use this as reference for the rest of the talk. OK, so this is actually an HTTP interface. And it also has a web API for you to create and manage game sessions and users. So as you can see to your right, you first start a session. And then you start your game. And then you play it. You can share it with someone else and play it together. It consists of two components. It has the backend component, which is the business logic for your container. And it stores all the state in DynamoDB. And then you have the front-end component, which is the AngularJS component. And it also has an Nginx proxy for serving all the static web pages on root and forwarding all the API path requests to the backend component. Cool. So we have this running locally. What's our next step? I want to run this on the cloud and productionize it. Great. So we're going to use something called serverless containers. But why? So about 5 years ago, containers gained popularity because of some of the benefits that it offers. First, all the container images are actually immutable. So whether you run it locally or you run it in the cloud, it just behaves the same way. That increases flexibility of your application. And then it also helps speed up build and release cycles. It makes your application stack or your fleet super flexible and efficient. Great. But now serverless is catching up. Why? Because it takes away the maintenance and operational burden for you to run your servers and actually manage them. It increases the speed for development. And it offers scalability and elasticity, and you end up paying only what you use. So I have this scorekeep application. Should I use containers, or should I use serverless? We have something better, which is Fargate, which is a perfect intersection of your containerized application meeting your serverless world. So Fargate is a compute engine. For those of you who don't know, it actually enables you to run Docker containers without having to manage your fleet of instances. So this helps you get the portability and flexibility of the containers, at the same time getting the zero administration and pay-per-use model of serverless. So today, Fargate is available as a launch type for Amazon ECS, which is a container orchestration service that enables you to run Docker containers on a fleet of servers. It offers functionalities like auto-scaling, service discovery, self-healing, and many more. So traditionally, with ECS, you had to bring your own instance that has our AMI. And it has Docker daemon running. It has the ECS agent running. And you had to manage the lifecycle of all the software updates that happen on that. However, with Fargate, you don't need to provision anymore. You leave the infrastructure burden to us, and you only focus on building applications that actually give business benefits to your customers. So just to rehash, Fargate's all managed by AWS, so you don't have to take care of instances. It enables elasticity, so you can configure rules that sort of scale up based on metrics and scale down automatically when you don't need it, so you only pay for what you use. And one biggest benefit, is that it's deeply integrated with all the AWS ecosystem, which customers really like, because they are familiar with some of these services like VPC, IAM, et cetera. OK, so no-brainer right now. I'm going to use my scorekeep application built on Fargate. So let's get started. I have my front end and back end. I containerize them, move them on Fargate. I add a a load balancer to it so that it can route all the traffic from the internet to the front-end container. OK, so to complete my setup, I need to think about 4 core building blocks. Starts with compute. So I need to think about how much CPU and memory will my container use? How is the volume going to be shared between the containers? Then I'm going to think about networking, which is how does my application connect to the internet? How would my application talk to other services in my VPC? Security, so how do I restrict my application to have access to only a few APIs or a few smaller CIDR block? So you can do that with IAM permission security groups. Lastly, and above all, is my application really running? Is it performing well? So we'll dive deep into visibility and see some of the tools that we have to answer some of these questions. But before we do that, I want to sort of use these 4 building blocks and apply it on a scorekeep application. So I start with an ECS task definition. Here I have 2 containers, back and front end. I have my Docker images pushed to ECR. Then I start with compute. I specify the CPU and memory parameters on my task and my containers. Then I have network mode, and Fargate supports AWS VPC network mode. And we actually create an elastic network interface and attach it to your task so it can talk to the internet. And for us to do that, we actually need task execution role for us to create resources in your account. Then we have security, which is, as I mentioned, you can restrict access to fewer resources in API, and you can do that with task IAM role. And lastly, we have log configuration. So we'll go into the details of how to set some of this up in a bit. So once you have your task definition, you just register the task definition, you create your cluster, and you create a service. And with this 3-step, you have your application running in the cloud. OK, but is it really running? Yeah, we need to have some visibility tools for us to know more about the health of the application. So visibility. Like I said, visibility is super critical for us to know if the state of the system and if things are working. Having an operationally excellent application helps you provide a good customer experience to your end users. At the same time, you have a balanced workload for your development team. So it's like a win-win situation. So today, we're going to learn some of the best practices for visibility so that you have some well-built running systems and all the tools that are available for you to debug. So there are 3 core visibility aspects. It starts with logging, then monitoring, and then we have debugging. So let's start with logging. OK. So it is important for you to know if your containers are failing, how are they failing, and why are they failing. So logging helps you provide additional context to your application. So you can do that by adding more state details or any transitions that are happening. And there's a fine line between providing enough context and providing a lot of context. So you don't want it to spam a lot, making it really hard for you to find the right information. So my recommendation to you is to have appropriate logging levels when you can. So use info for giving the right amount of information. Use debug if you really want to go step by step to sort of help with better troubleshooting on an edge case situation. Or if you have errors, classify your errors. Which ones are fatals? Which ones are errors? Which ones are warnings? So that you can actually create alarms of those and have different thresholds for each category. OK, but we are using a serverless application. Our inspecting logs in a serverless application follows a different model. Like you have no longer access to a production box where you can SSH in and grep for log files. So what you need to do is actually push all these logs into an external logging driver. And with Fargate, we have support with Amazon CloudWatch log driver. So you can push your logs out to CloudWatch and have a look at it in CloudWatch. In addition to application logs, you can also trace any API requests that your application makes or any other user makes in your account. And you can do that using CloudTrail. And it's super useful for auditing purposes. And then when a request does go through multiple steps, you kind of want to trace that request end to end. And you can do that distributed tracing using X-ray. OK, so let's go through each of these and see how we can set it up. So Amazon CloudWatch. Like I mentioned, we have AWS Logs. This is the log driver that you would use to actually set it up. And then our first step is to create a log group in CloudWatch. Once you do that, you configure your log driver in your task definition, and you're ready to go. Oh, one more thing. Remember to add permissions via your task execution role so that Fargate, remember, has to push those logs into your CloudWatch console. So we need permissions to do that. So once all of this is done, your logs are getting published, and we natively have support to tail your logs inside the ECS console, and that's a screenshot of that, where you just go to a task, look at the logs tab, and then pick your container, and you just see the tail live logs. Cool. So then we have AWS CloudTrail. And what that does is any APIs that you use with ECS automatically get sent to AWS CloudTrail. So this is super helpful for auditing purposes. In this example, as you see, I actually made a describe services request, and then you see all the metadata around it, around the request payload. So you have my header, you have the source IP, you have the IAM user I use. So you can actually troubleshoot to know if this was accidentally made, is it a suspicious activity, and you can use this later for troubleshooting. Remember, you can also create alarms off of these, so if you're not expecting an API call to be made, you will be able to trigger alarms and get notified. This is something I'm super excited about, distributed tracing, because X-ray integration with ECS was announced recently as last week. So what this enables you to do is actually trace your request all the way down. So how do you do that? You first create a Docker image with the X-ray agent. And once you do that, you add manage policy to your task IAM role so that all the daemon can actually publish the trace data to X-ray. And then you update your task definition and run this daemon as a sidecar container. Update your task definition, call update service, and there you can see visualization on how an application like Scorekeep and how a request goes through different API calls that we made with DynamoDB, for example. And not just tracing it, you actually get instrumentation as a side effect. Now you can see how much time is actually spent in each step of these calls, so you can go around optimizing some of these and reducing the latency overall. So this is super useful. OK, so we've seen some logging mechanisms. Our next step is to move on to monitoring. So monitoring is really important to understand the health of your system. Now, we like to preemptively measure everything, emit metrics for everything, so that we have it when we actually need it. And an operationally excellent perspective, metrics allow you the ability to actually look at what your service is doing in a near real-time fashion. And it also helps you sort of evaluate changes that you're making through deployments. Is my performance getting worse? Is it getting better? So it enables you to do rollbacks quickly. And then it also helps you sort of forecast future growth looking at your current projections. And when you do things like that, you can actually preempt any scaling issues. And metrics in general is just helpful for you to troubleshoot and know when a problem does exist. OK, so to get the ball rolling with your application, when you have an application, some of the key metrics that you need to think about are latencies, your server exceptions, your client exceptions, CPU and memory to identify load. Then if you have a load balancer, which we do in case of Scorekeep, then what you do is look at the request count and the connection count. Also an indication of how my application is being used. Do I need to scale it up? Do I not? And then if you have a dependency, it's super important for you to have metrics and profiling just around that dependency. For example, if you're using DynamoDB in our application, I want to know the latency and throughput of just that particular API call so that if there was an issue, I can just pinpoint to one small dependency. OK, so by default, ECS provides CPU utilization and memory utilization out of the box. And we have seen trends of customers consuming these metrics and actually configuring auto-scaling rules. So when your CPU utilization spikes up, you know your one container is actually doing more than it actually can. So you'd use that metric to scale up your service. And when you think the load's gone down, the traffic's smaller now, then you would scale it down automatically. And remember, This is all serverless, so it happens instantaneously. You don't have to wait for your servers to come up and then your containers to get placed and your servers to go down. It's really elastic, and it can cater to your needs immediately. That way, you only pay for what you use. And in addition to these metrics, you can always emit your own custom metrics and create CloudWatch metric filter out of those. Oh, this is a screenshot of the CPU and memory utilization that ECS automatically provides, and you can see like the minimum, average, and maximum to sort of get a range of how each container is doing. OK, so we have our metrics flowing. Our next step is to actually create a dashboard for this. So we want a single view of all these different metrics that we can correlate them in one single page, so that it's just easier when you're going through them in operational meetings for you to identify some failures or some improvements. So CloudWatch, by default, offers you some default dashboards for all the services that you use. So this is an example of my scorekeep ALB that I use. And then you can see the request count going up, connection count going up. So this is useful for me to like view multiple things and correlate and like just draw lines, and easy for me to identify things. But in addition to default dashboard, you can always build your own custom dashboards. Now, you may ask, what do I put in my dashboard? I think it just depends on you. You decide what goes in it and what doesn't go in it. And I think a dashboard is generally catered towards the audience. So for example, you are a subject matter expert. You build scorekeep. You may use your dashboard as a run book. So you will probably want to see the last 5 hours and see how, if a latency spike happened, if it correlates to a different dependencies, or is it some other problem that's isolated to just one container. So you will be able to see more, and you probably want a view that's much more shorter. At the same time, if you were someone who's like looking at trends and forecasting capacity or something else, then you need to sort of view your graphs over 2 weeks, and you're looking at request metrics or fulfillment metrics. So you need a different dashboard for that. We are also partnered with our third-party vendors like Datadog, where if you had a sidecar container with Datadog agent running, then it actually profiles more and emits more metrics, and it helps you visualize something more granular as you see over here. So it's really helpful, and based on your application, you can always integrate with Datadog. OK, so now we have our pretty dashboards to look at, but you still don't want a human to go through each of these dashboards to detect problems. What do? You actually create alarms to trigger if your SLA is breached after a certain threshold. So some of the common alarms or basic alarms that you need to create should answer these questions like, can my customer actually access my service? Are my customers getting the right response? Are my customers getting the response fast enough? So these are some common alarms that you create so that you can identify the problem before a customer actually identifies and reaches out to you. And you can create these alarms on CloudWatch console. And when you do use CloudWatch, you can also take some automated actions out of these alarms. So you can either notify you're on call and page them, or you can take automated actions like autoscaling, as I mentioned earlier. Some other monitoring tools that are helpful are to notify state changes. So a task in ECS goes through a life cycle, like it goes from pending to running to stopped. So ECS, by default, actually emits all these state changes to CloudWatch events. So it looks something like this. This is an example of when my task actually stopped. And you can see the stopped reason. It was because there was a scale-down activity that happened. This is really useful for me to know when state changes happen, so I don't have to constantly poll an API to figure it out. Now, what do I do with this information, right? So with this CloudWatch event, you can create a rule that does multiple action. For one, I can put it in CloudWatch logs or in S3 so that it's there for auditing purposes or for troubleshooting later. Or some of the things that you can do is actually, if you are running unmanaged tasks, and if you think, oh, my task actually died, then I need a replacement task for it. So you can just use Lambda to consume this event, describe your task, and get all that information and run a new task. So there are so many automated actions that you can actually take for this. Super useful. And then you have container health checks that we launched earlier in the year. where with ECS, you can configure health checks in your task definition. So you can tell us the command to run, and with constant ping checks, and if your deep ping checks are failing, then ECS Service Scheduler will actually replace this unhealthy task for you. OK. So we have all these monitoring tools that are telling us that something is going wrong. So when an event does occur, we need to know how to diagnose it. How do we actually root cause it and correct it so that we prevent it from happening again? So our debugging tools start with our APIs and console. So if a task stops, you need to look at why it stopped. And our APIs provide information for you, like the stopped reason on a task or a container level, exit codes, so that you know which is anticipated, which is not. Like I mentioned, the state changes a few slides ago. That's something that you can always look at to know why a task stopped. But if a task never started, you can also look at service events in describe service payload or in the console to know why my task didn't start. Let's look at a few examples. OK, so debugging task limit exceeded. For those of you who are unfamiliar, Fargate has a default limit of about 50 concurrent tasks in a region per account. So if you ever run into this, your error will look something like this, where you see we've reached the limit on the number of tasks you can run concurrently. What do you need to do? You need to request a limit increase. But a couple of tips for you is when you do run into this, it's probably too late in your application. You want it to be scalable immediately. So if you're looking at forecasting and thinking of a big use case that's coming up, I suggest you reach out to us earlier so we get the lead time to actually make the request happen. The second thing is when you're requesting for Fargate task limit increases, think about your application as a whole. Think about all the other pieces where you need to increase your limits. So if you're using ELBs, or ALBs, I should say, then you need to go increase your target group limits. If you're using public IPs, then let us know about that. If you're using your VPC and subnets, make sure your address space allows for enough IP addresses for these tasks to take up. So those are some common errors that we see. OK, let's look at another one. Debugging container pull error. Maybe some of you have already encountered this. So here's my situation. I have a service. My desired count is 55, but my running count just stays at 26. Something seems to have gone wrong here. OK, so I look at my service. I look at my stopped tasks, and there are some tasks that are stopped because it fails to start. OK, so let's look at one such instance of the task. And then you see the container reason, and it says it couldn't pull the container. Then I look at the details of the error, and it says that, oh, there was a timeout that happened. That instantly makes me think that it's actually a networking error. So I take my subnet ID, I go to the route table, and what do I see? I don't have a route to the internet, so no wonder my task couldn't pull the image. So I add a route to the NAT gateway. It goes to the internet gateway, and my service was able to start new tasks. So we have more situations why your container pull might not succeed. They could be because of permission issues, or you might be using a custom DNS server with some stale records. So we have enumerated some common errors that you can always look into our troubleshooting guide for reference and solutions and how to solve them. OK. In addition to our APIs, we also published our own application logs. So if something does go wrong, you have a way for you to go to the CloudWatch console and look at it in depth. You also have tracing mechanisms that we showed. So if you had a request, go to X-ray and look at all these paths that your request hit. And you can also use CloudTrail to know what happened to a task. But if you are someone who wants something more sophisticated, a lower level, like Docker level constructs, you can use ECS's feature called Task Metadata API. What that does is you can actually query for more information by hitting an endpoint that we expose from within the task itself. And that provides you more stats about the task. It gives you the environment variables that were resolved for it. It gives you Docker labels. And this information is something our partners like Datadog actually use to publish those metrics in the dashboard that we saw a little bit earlier. So when you do hit that endpoint, you will get a metadata response that looks like this, where you have the Docker ID, you have like more labels, you have more granular statuses that are out there. So you can use this for you to troubleshoot more. OK, so let's conclude. Some of our takeaways here are that monitoring, alarming, logging are super critical for you to measure the health of the system. And Fargate is actually a container runtime that enables you to run something serverlessly. And when we do that and we lose control or access to our hosts, we still have so many tools within the AWS ecosystem that actually helps us get greater visibility into the containers itself. So with that, I'd like to hand it over to Carly to talk about Catalytic's use case.
Thank you.
Yeah.
Hello, can you hear me? All right. I'm Carly Cindy. I'm a software developer at Catalytic Data Science, also trained as a molecular biologist, spent about 10 years in the lab, from vector construction teams to epigenetics, and essentially just collecting and analyzing lots and lots of DNA and RNA. For the past several years, I've been writing code to make the workflows in these labs a lot more accessible and easier for the researchers who are doing them. And this is exactly what we're doing as well at Catalytic. We make software for life science companies, and our goal is to make it easier for the researchers at these companies to discover and improve upon therapeutics, as well as make advances in other areas, such as crop science and agriculture. In order to make these advances, the researchers need access to a lot of different resources, such as scientific literature, patents, regulatory documents, data. Lots and lots of data. They generate a lot of in-house data, as well as open access published data. They need tools to analyze this data, as well as a way to collaborate with their colleagues on their findings. So generally, all of these resources are spread out, siloed into different softwares, and they're tough to use at scale. So at Catalytic, we've brought them all together in one R&D cloud platform and behind one secure web application. Today, I'm going to talk mostly about the data analysis tools that we have. They're all Dockerized and all running on demand thanks to Fargate. Analytics I'm going to really dig into here is called Magpie. And that is short for a multiplexed automated gene editing pipeline. I'm going to talk about our implementation of Magpie with Fargate from prototype to production. Also going to give a little bit of background on what Magpie is doing. It's analyzing data that the researchers are generating from performing gene editing experiments. So gene editing. It's been around for many, many years, something like 40 years. But it's not until recently, the past few years, that it's become really more site-specific, so a little bit more exciting. Who has heard of CRISPR? Raise your hand. Yeah, so CRISPR is one of these gene editing systems that's site-specific. And this is so exciting because most disease is caused by mutations in our genes. And most therapeutics only address the symptoms and not this underlying genetic cause. So a gene, it's just a portion of the DNA. It could be thought of as a string of varying length made up of 4 characters, A, T, C, and G. If one or more of these characters gets removed or added in, inserted in, or swapped out, that is a mutation. And that can lead to disease or possibly an advantageous trait for that organism. Here I'm showing a portion of the gene that codes for hemoglobin. And you can see in this next string that that A is switched to a T. So that's an example of a mutation. And this exact nucleotide, this exact point mutation, this one character changing from an A to a T, if that happens in both alleles, that causes sickle cell anemia. So wouldn't it be great if we could go in there and change that T back to an A? And that's exactly what these gene editing systems are capable of doing. So this is just one example of one of the experiments that our researchers, or the researchers that use our software, do. So what they perform these experiments, and then they will generally have a result of the repaired ideal result that they're trying to get, and then the non-repaired, or maybe some other offsite cutting or inserting. So what they want to do is optimize that repaired result. So they can make slight modifications to the gene editing system, to the other variables, and then when they perform this in cells, they have to collect the DNA and then send that off to an NGS lab. So NGS, that stands for next generation sequencing. So they'll send off this DNA. The lab will sequence that DNA for them and send it back to them in the form of flat files that contain hundreds of thousands to millions of strings. So now they need a way to analyze these files to determine which condition gave them the outcome that they were trying to obtain, and that's what Magpie does. It takes an input of a reference and then a flat file that has hundreds of thousands to millions of reads. It aligns those reads, those sequences, to the reference and then finds the areas that it differs from the reference. There's a lot of other pre-processing that's required for NGS. Each of these characters has a quality value associated with it, so that needs to be quantified. The user can input a parameter dynamically to change the threshold of that quality. So if that quantification doesn't end up meeting that threshold, that string, that sequence will be thrown out. There's also smaller strings on either side of the sequence that they're interested in that needs to be identified and trimmed off. And so there's after all those pre-processing steps that Magpie does, then we'll do the alignment, and then we'll look for the areas where the sequences differ from the reference, do some quantifications. It uses NumPy and Pandas, Matplotlib, and it creates some really nice visualizations, really good insights for the researcher into the performance of these different experimental conditions. Also has some raw output files as well. So this application can take a while. Our user came to us and said, you know, we'd really like to speed up this part of our research workflow. Can you make this faster? At the time, we were running it on an EC2 instance. And so we knew that it was CPU bound, so we bumped up the instance, we increased the threading, which also increased the memory. We were not too worried about that at the time. And so we were able to decrease the processing time by half, which was great. But the customer came back to us and said, you know, we have 40 of these files that we have to run through this application, all representing the different experimental conditions we're trying to compare and figure out which one is the ideal one, and then we can go back to the lab. And this is really, we're having to put these through this application one at a time, and if Magpie takes 20 to 30 minutes, you know, that's a 20-hour analysis by hand for 40 files, and we just really need to speed up this part. Can you please make this even faster? So that's when we knew we needed to take a step back and figure out how to run this application in parallel. We'd already been kind of thinking about this. We wanted to go serverless with some of these analysis tools anyway, because they were, like I said, they were running on these EC2 instances, and so that we're kind of paying for it constantly. You know, we're not just for it to be available. But they could, these tools were all Dockerized. They could run from a Docker run command with some runtime override parameters. And so we only really needed it to spin up when we passed in those files, those parameters, and then when it was done, it could just go away, and we didn't want to continue to pay for it. So we thought we could do both of those. We could only be paying for it while it's being used and offer or offer parallel runs at the same time for our customer. So we looked at what AWS had to offer at the time to be able to assist us in this. We knew we wanted to use ECS. We thought about EKS, but we're a small team. We didn't have a lot of expertise in Kubernetes at the time, so ECS it was. When you think of genomics and life science and AWS, a lot of times you'll think of batch. So we did consider batch, and it would have worked really well for some of our use cases. But again, being a small team, we wanted some technology we could learn that we could use throughout the platform and optimize all areas of our platform and not have to maintain different tools in our architecture. So we were really excited about Fargate. So this is how we set up our prototype architecture. The files would hit an S3 bucket. That would trigger an S3 event that would spin up a Lambda. So Lambda, not normally what you think of for a compute-hungry, long-running process, but all we were using this Lambda for was to pass along the task definition that we'll talk about again here in the next couple of slides, and any override parameters, and pass that off to Fargate, and then Fargate would be responsible for provisioning and pulling up the container and any networking and any scaling that we had to take care of. So it could automatically handle all of that. All we had to worry about was getting those files to S3. 40 files hit S3, 40 events would happen, 40 Lambdas would spin up. Those would all go over to Fargate. Fargate would spin up 40 containers with the appropriate resources. So this worked really well. Once those containers finished, they would write any files back to S3. And so we were happy with this prototype. We were able to run all of those, run this application in parallel so that all those containers were running at the same time so we can get those results back to the customer. Some kind of an unintended benefit is this parallel runs means parallel results. So now we created this UI for the results that the user could view. So once these were finishing, we were able to parse out and pull out the important results, populate this table, and then also had some hyperlinks to dig a little bit deeper. But now the researcher doesn't have to leave that research mindset. You know, before they were spending days just logistically taking a file in, going in, copy and pasting the important results to an Excel sheet. Now they just drop their files in, click go. They're immediately, as they see this results table being populated, they're building new hypotheses and breaking down other ones, and then they're able to, within the same day, go back to the lab and start making different and better genome editing systems. So that was really huge. And not to mention the automation, automating the human error of copy and pasting results and all of that. So we were really excited about this. Another, also specific to Fargate, it's very good for the user behavior, the sporadic application load that we see with our analysis tools. So we'll see lulls of usage. People basically won't be using the tools, and then all of a sudden there'll be a big peak, and that's just the nature of their job. They're spending areas or long amounts of time in other areas of the platform, looking at patents, looking at scientific literature. Then once they hit on that experiment, that genome editing system that they want to run at scale, then they'll send that off to the NGS lab, get those files back that they want to analyze. So now, instead of paying for that EC2 instance to be up the whole time they're just doing their background research, we're only paying for when they're hitting our analytic and per second at that with Fargate. Also with developer time, this was trying to code for that type of sporadic application load would have been a challenge, and Fargate is able to take care of that for us so that we were able to get that back to the customer and meet this customer request really quickly. And then back to the initial request of, can you make this faster? They can now run 40 files in the same amount of time it previously took them to run one. So that made them very happy. Lessons learned. I'm going to talk about the CLIs on the next slide. Definitely want to plan for limited task size and quota. So 10 gigs disk space, 30 gigs memory. We can get pretty close to those limits with some of our applications. So we will process things in memory, and we take advantage of streaming to help out with some of that. Quota. So I believe the quota is now at 50, but when we started it was at 20. And again, all you have to do, and that's the number of tasks you're running in Fargate. And so all you have to do is request an increase, but bear in mind that this is per account, not per VPC. That threw us off a little bit at the beginning, so Be aware of that. Reduce your Docker image size. So Fargate doesn't take too long to spin up, but it has to pull down the Docker image from wherever you're storing it, and we store ours on the ECR. So if your Docker image is large, it can take a while to pull down onto that container that Fargate has provisioned. So definitely take advantage of the different resources out there. We love, like, multi-stage Docker files are awesome, and there's lots of minimal base images to start off with. So just try and minimize the size there if you can. We also wrote a cron job to, if maybe one of your applications is running suboptimally and it's a memory hog or there's some bug in it, you don't want it to be paying for it just to be like chugging along in Fargate for days. So you want to be made aware of that so that you can get in there and then optimize that application. So the CLIs, there's a couple official CLIs, ECS CLI and AWS CLI. There's also a couple unofficial that I've heard good things about. I'm going to talk mostly about the ECS CLI today. It has a compose feature, which is pretty cool. You can run and set up tasks with Docker Compose-like commands. Here is an example on the right is the Docker Compose YAML snippet. Looks pretty standard for a Docker Compose file. Not all of these items map to something that, for everything that you need to set up a task, so you need an additional ECS params YAML file, and both of these files for us live in each application for each of our tools, each of our microservices. And we just use this to set up the task on whatever cluster we identify. You can run from these two files. You would just use a different command. We use ECS CLI compose create, but you can use compose up or compose start, and then you would go to the console, show a screenshot of that, and you'll see your task actually running. But in this instance, if you use compose create, you'll just see that task definition there, but nothing running. So let's talk about what you need here. Network mode, AWS VPC is required for Fargate. Your task role ARN, so any permissioning, if you want to restrict or allow with your containers that are going to be in here. The execution role, so you'll need this for accessing the ECR, or if you want to log to AWS CloudWatch. Task size, so this is the limit that you're setting for the task and any containers that is within that task. These two, the CPU and memory, those are on a sliding scale, so just check the docs for which pairing of these limits are appropriate for your application. Services, that's not ECS service, that is referencing the services you have defined in your Docker Compose file. You can also get a little bit more granular once you define your service. You can get a little bit more granular with those task limits. You can, if you want to limit one container to, I only have one container identified here, but if you have more images that you're going to be identifying or more services, you can get granular with the task and give more memory to one and less memory to another one. So that's pretty cool. And then the run parameters. So this is the subnets you can identify, which is really nice because they will, if you don't, you can have your containers communicate with each other within that VPC, and no traffic will leave that VPC if you want, and so that's really convenient. And then over to the Docker Compose file, just a little note, there's a little bit of difference between version 2 and version 3, mostly just where it defaults to. If you have an item specified in both your ECS params and your Docker file, generally your ECS params will override, will be take priority if it's defined in both places. Your image, the ports, and you want to make sure you have logging or it's not going to log, so you have to have that identified. So that's how we create our task. It's just up there. It's not running yet. As I showed with our architecture, we use a Lambda to actually run it. And you can see this is all pretty generic environment variables, so we can keep this in a Fargate service, and that's what we do. And we only have one Lambda to rule them all. So that's really nice because you don't have to maintain a lot of different code, right? You can just have this one Lambda that if you want to make any changes to, that will be experience throughout all the other analytics. So, because we do some other like exception handling and stuff around this code. When we have most of our Lambdas written in Python, so we use the Boto 3 ECS client to actually run the task. And so you'll need to identify your cluster, the task definition that we just talked about, so any runtime overrides. So a good example would be where that file is, or that quality threshold that I talked about. So anything you're overriding that are defaulted in that container. Launch type is Fargate. You can actually change this to EC2, and you can like exec onto your container and do some troubleshooting, and then change it back to Fargate when you're ready for the benefits of Fargate again, and then your network configurations. So now I'm going to show some screenshots of when you go into your console. So this one you can see, you will see it pending, so that's like while Fargate is provisioning and figuring out resources and all of that, but that's not too long. Soon it'll be in the running state. And then this, you can see there's one running task, and that is essentially for us means there's one file that hit that architecture. And then you can click on that task, and then you can see the items that you defined in your task definition, just confirm that that's what you meant to do. And then you can go a little bit deeper down into that actual container, and those, you can see your overrides. You have a link to the CloudWatch logs. You can actually view the logs directly in the console. So that's really nice to get some confirmation everything's running the way that you meant for it to be running. So with our prototype, we knew we had some significant limitations, and so we set some requirements for ourselves for our production version. One of the big ones is our Lambda was essentially blind. It didn't care whether the container finished successfully or whether it hit any infrastructure error. It just sent off that task definition, then was like, I'm done. So we needed a way to retry that. Recalling past processes. We definitely needed some persistent data, especially as we decided, or we're going to make some workflowing some of these applications together, and outputs of one application would then be used as the input of the next and have some choices and input from the user. So we definitely needed to have a way to have some persistent data that we could have those later applications recalling what happened earlier on in the workflow. Visibility. We need to know why something happened, when something happened, and how to address that. So that was also a consideration that we needed to figure out. So this is what we ended up with our production version. The files, again, would hit S3. We would write some metadata to DynamoDB. Now we're using step functions. Step functions was really nice, especially as where we wanted to see this growing into. And we were essentially using step functions at this point as an orchestrator for the Lambdas. The Lambdas work the same way. They pass off a task definition and any overrides to Fargate. But now, if there's an error in Fargate, an infrastructure error in Fargate or Lambda, we can now retry that with step functions. So once that container runs successfully, then those files would be, the results files would be back to an S3 bucket, and then any metadata would be written to Amazon DB, DynamoDB. So this worked out really well. We've been really, really pleased with this architecture. Again, users upload some files, those run through that architecture, and then we can provide those results back to them really quickly. The next thing that we've been working on is workflowing these applications together. And we've got, this is an actual example of one of our workflows where we have 5 of these Dockerized tools running in parallel, and then one final tool that will essentially take all of those results, make some visualizations and outputs for the user. And we run this at the scale of 400 samples. So that means that 400 files essentially are hitting that first tool, passing on, going through that architecture, passing on those task definitions to Fargate. Fargate's spinning up 400 containers, and then for that task definition, and then for each consecutive tool that we have in the workflow. So it just sets it off, and step functions can control and what environment variables get passed on through that Lambdas. So that's been really, really exciting to see that kind of coming together there. So let's talk about visibility. With any errors that we see or that we populate the results table with, we are generating an endpoint using DynamoDB. So we will write we actually write to DynamoDB inside the container, so we can parse any error messages that are specific to the application to DynamoDB, and we can capture infrastructure errors as well by essentially assigning that call to the Boto3 ECS client, and then parsing that, and then we can write any errors here, and the same for Fargate. So the Lambda is then essentially writing some error messages here. So we can use, this is really, really informative in a bunch of ways. Like, there's a great CLI, and then we can also get some insight into some of the common errors, like user errors that our applications, that our users are doing with our applications, which is nice because we can, for the really common errors, we can maybe add some tooltips or modal to help them kind of avoid those errors. And then obviously catching the infrastructure errors that we need to retry if we're not already catching those and retrying them. So the Step Functions Console is really nice and granular for monitoring. So if we see we have an error and it's in one of these really complex workflows, this is a pretty simple state machine from Step Functions. It's essentially like 3 tools that are that go consecutively, but there's lots of like complex state machines you can create with Step Functions with choices and branching off, and it's a pretty cool tool. So, but we can, with the error, we have a unique execution ID that we can then go see the actual step function, the state machine, from that execution, and we can see where it failed, and I'll talk about why it failed. Well, we have an example of that too. And then the ECS console. This is a really straightforward way to get in there and see if you've created the task and the cluster the way you intended to. One thing I want to make clear here is that I've got 2 clusters. I've got demo tasks, and these are ephemeral tasks that will just spin up and then spin down. And that's pretty much everything I've talked about today are these ephemeral tasks. And so you'll see there's no services defined in this cluster. In the other one, you've got just demo, you have services, and those are constantly running, and that's like where the Lambda is living. So one of the things you'll note here is that the ephemeral tasks does not have data associated with them. So, but with the services, you do get some really nice output with the metrics. But you can grab task-level metrics using Datadog, but you don't have that through the console just yet with ECS, so just keep that in mind. So with debugging, we do write the error message to the Dynamo as well, so we can identify at that level if it was application or if it was a generic error message that we need to dig a little bit deeper into. And then with the Step Functions console, as I showed the same screenshot earlier, but just expanded it out a little bit, you can actually click on the error, and then you can see where we log what the error was. So we capture that and log it here. And so we can say, oh, OK, this is capacity is unavailable, so we've hit that quota. OK, we'll set that up, and we'll retry that until it's successful. And then also ask for an increase. And then this is an example of an application error. We write the ARN, so the Amazon resource number, and then we can go to CloudWatch and dig a little bit deeper into those logs. And if your container is killed or if it dies for some reason, you still get partial logs. So it's really convenient for that if you can't already tell what's going on with some of the other tools. So just want to, at Catalytic, we're always trying to make our process better and always trying to make the experience better for our users. So we think some things that could help with that is maybe making the infrastructure around Fargate a little bit more fire and forget. So with rate limiting and those quotas, if we could have some automatic retries, that would help with that, as well as mounting a larger volume than the 10 gig EBS that is already there would be really nice for some of those applications that require that. And then the task level metrics in the ECS console. So thank you so much for coming to this talk, and please go to the app and fill out the survey. Thanks.